Great, thanks very much. I wanted to acknowledge my co-author, Jennifer Scully at JPL, and others not listed here who contributed to this work. We wanted to present a perspective on the potential utility as well as the accessibility of these so-called micro-cold traps at the Artemis 3 landing sites. Next slide, please. So this is a one slide summary of lunar polar volatiles, which I realize is ridiculous, but here's my attempt. Basically, we know that there is evidence for exposed ice on the surface of the cold traps where we would expect it to exist at temperatures less than 110 K or so. Um, the coverage of that surface ice is not uniform, but it correlates well with temperatures acquired at spatial scales of about 300 meters by Diviner. In contrast, the hydrogen abundance, as measured by neutron suppression at roughly 10 kilometers and larger scales, is poorly correlated with surface temperatures measured by Diviner. There is some correlation in the sense that the temperatures decrease towards the poles and the amount of hydrogen also increases towards the poles, but the exact locations relative to the known larger PSRs and cold traps therein, that correlation is not as strong. So how do we reconcile these observations? And I'll just mention that the plot on the right is meant to reinforce the first bullet, which is that when you look at the surface reflectance and the signature of that we'd expect for water ice in the UV to near infrared, those data sets indicate this jump at in those metrics at temperatures below 110 Kelvin. Next slide, please. So one thing we have to consider on airless bodies like the moon is that temperature is controlled almost entirely by topography and insolation on those sloped surfaces, as well as the scattered radiation from nearby illuminated terrain. And so we need to reframe our thinking about what temperature really means relative to what we're used to in our everyday experience on Earth. So there's no atmosphere to even out these temperatures. There's a further set of factors on the moon that make the thermal environments even more extreme. And this is the combination of the slow rotation period. So for the moon, this is about 29 and a half days, and the insulating nature of the regolith. So that low of a thermal inertia means that you can maintain huge temperature gradients on scales of millimeters. And so we expect these kinds of temperature gradients down to scales well below what has been resolved from orbit, and really requires in situ measurements by astronauts and other surface assets. So next slide, please. So we can model what the temperatures would look like at locations such as the candidate Artemis landing sites. Here's an example. So you can see what a random rough surface would look like when illuminated at a glancing sun angle on the right, and then what the temperature distribution looks like on the left. So you can see this is the number of surface facets having that particular maximum temperature over the diurnal cycle. So what surface roughness does is it basically it spreads out the distribution of temperatures. And I think I misspoke. This is an instantaneous temperature distribution, not the maximum. Next slide, please. So that's the context for previous. Yeah, that's the context for the concept of micro cold traps. And you know, there's I think a little bit of ambiguity in the definition of micro cold trap. And here's one possible definition. So these are small shadowed regions that are unresolved from orbit, where water or other volatiles may be thermally stable. And I define these, or we define these as contiguous regions of scale 1 centimeter to 10 meters in horizontal extent, with maximum temperatures of less than 110 Kelvin for water stability. The modeling work done previously has shown that these should be ubiquitous, meaning on every sunlit surface poleward of about 80 degrees, you should expect array of micro cold traps of different sizes. And we also note that there's an important distinction between the micro cold traps and their larger cousins, which is that they are by definition shorter lived, and that's because of their small sizes and low volumes for actually trapping volatiles. So the regular gardening of the regolith will bring up and destroy volatiles near the surface, and so the population of micro cold traps is by definition younger, and therefore provides a separate chronometer to the deeper ice deposits if they exist. Next slide, please. So in terms of the thermal environments of the candidate landing sites, they're all poleward of about 84 degrees latitude, so all within this micro cold trap region. And just pointing out here that even inside of PSRs, the temperatures oscillate quite dramatically over both the diurnal and seasonal timescales. So you can see the example there where the exact temperature at any given time is a complicated combination of local topography effects that is very dependent on the exact location at all spatial scales, but it generally follows both the diurnal and seasonal oscillations. Next slide, please. So again, referring to the diviner data and the micro cold traps modeling work that we've done previously, looking at the range of latitudes where the candidate Artemis landing sites exist, you can see the lowest latitude one and the highest latitude one indicated there. We expect a range from 10 to about 50% coverage of micro cold traps on the surface. Again, this is within terrain that is otherwise illuminated on a flat surface. Next slide, please. So we looked specifically at the Malapert landing site, and this is a model done with the 2-meter digital elevation model, including the illumination over the course of the entire diurnal cycle. And you can see that of course, the illumination conditions are highly local, again, as I've said before, and we can estimate the numbers of PSRs of different sizes. So there's, again, just order of magnitude, roughly 10 PSRs greater than 100 meters and hundreds less than 10 meters. And then as you go down in scale, you get more and more. So thousands of micro cold traps less than a meter are anticipated within the 2-kilometer EVA area. Next slide, please. This is a different perspective on the same model. And this kind of illumination model is like, sort of the boundary condition on the thermal models that we use to predict volatile stability. One thing that's important to note also is that, given, I think Malapert is an interesting example here where we have an equator-facing slope and a pole-facing slope with a ridge that divides them roughly in the longitudinal direction. So you've got a cold slope and a warm slope, and that's very interesting from the perspective of collecting samples from these micro cold traps, where there should be a preponderance of them on the pole-facing slope, which is in the upper left in this map, relative to the other slope. Next slide, please. So we also have to consider the geologic context of each of these sites, and this is just a summary of that data for the Malapert site. This is because, of course, meeting the science objectives of the mission depend not only on the volatiles questions, but also on the more geologically oriented questions. And so how do we define a traverse or set of traverses on multiple EVAs that will accomplish both those or all of the objectives? And so this is sort of the context of that. So as I said, this central ridge that cuts across this region includes a variety of different crater ages, of different sizes. We have impact melt and boulders that are accessible within that 2-kilometer region. And the slopes on these larger scales, which are illustrated dramatically in this oblique view from LROC, again, are important for determining the local thermal environments of the micro cold traps as well. So let's move on to the next slide. So in terms of the
2 minutes, Paul.
Thanks.
2 minutes.
In terms of the accessibility, the larger PSRs, are easily resolved from orbit, and in even the coarser digital elevation models, we have to make predictions for micro cold traps, hundreds of times more abundant in the next decade of size range below that. So as you step down, you can see in the plot here how the number of micro cold traps per unit area increases with decreasing size at this latitude. Um, in terms of the types of samples that should be acquired of micro cold traps, it would be interesting to get a drive tube sample of a 1 centimeter PSR, but the information below a few centimeters depth won't really be relevant. So the scoops and the contact samples in the upper surface would be the most relevant for the micro cold traps, but then comparing the volatile content there to similar samples from the larger PSRs. One thing that we've considered carefully, Jennifer and I, is the contamination of these PSRs of all different sizes from the landing itself, where this could be seen as both a problem and an opportunity. We have the chance to study how volatiles of known composition from the thrusters are trapped in these regions of all different sizes. So that could be quite interesting. How to identify micro cold traps and PSRs in real time, that's addressed on the next slide. So I'll summarize and then get to that last point. So the micro cold traps are much more numerous than the larger cold traps, and therefore they will be encountered at any of these sites. These illumination models and thermal models that we've done show good agreement with the predictions based on the extrapolation from the diviner observations to smaller scales. We propose that near real-time DEM generation could be done along with the 3D thermal modeling. We've reduced the computational time of these types of models down to a few hours now. And so this could be done with knowledge of the topography from photographs from the surface, for example. If there is some latency where we can't get that data right away, you can still estimate the likelihood that a shadow is a micro cold trap based on the slopes and sun angles. So comparing these samples to larger cold traps provides an interesting way of measuring the present day or recent past influx of water to the moon compared to the deeper deposits. Thank you very much.